Let's take a moment to set the stage for what we're going to discuss today. God made the earth to be inhabited, and He made the sun, moon, and stars to keep track of times and seasons. It's all a perfectly designed clock and calendar. The Lord made the sun and the moon, and He set them in the firmament of heaven to divide the day from the night. And all these things that He made, He designed to suit the inhabitants. With these things in mind, we're going to ask two simple questions. What foundation did He establish it on? A ball or a flat plane? And what keeps the light divided from the darkness? We'll answer these two questions through observation of sunsets, that point of division between light and darkness, day and night. Then we'll reason through the process of elimination. If the separation of light and darkness can't be observed on either the ball or plane, then that one is ruled out, and the other is by default the established foundation. God separated the light and darkness. He also set the boundaries of the light and darkness. The foundation will establish the type of light used and what limits it. On a ball, it's the earth itself that blocks the light and causes darkness. On a plane, it's a limited reach of light that causes darkness. The fading light you're seeing on your screen presents a geometric problem on a globe. In other words, the geometry doesn't work. You see, this occurs 1.5 hours after sunset, and the spectator who saw the sunset has been spun on the earth 1,500 miles into the shadow of the earth, and now has a curvature issue, a section of earth 280 miles high between himself and the terminator line. He can't observe this event. Here's an animation to emphasize the reason why he can't see the lower atmosphere, that 280-mile high gap between the spectator and the lower atmosphere, where the sun's light shines across the rim of the earth. The spectator is 1,500 miles into the shadow. He can't see the glow of the sun in the lower atmosphere. 1.5 hours has passed before the image in the lower right of your screen occurs. And this baller now has a 280-mile high obstruction between himself and the terminator line where the sun passes over the earth. He can't see that orange glow. In this video, we'll talk more about the reasons why people on a spherical earth wouldn't see the light fade after sunset. And also, we'll talk about what's likely limiting the sun's light over a flat plane. Today, we'll look at the world outside of the box. Hi, my name's Steve Matthews, and I'll be your host, also known as Teeth of the Lamb, and today is March 30th of 2022. The title of our video today is The Light of the World Exposes the Ball Earth as a Fraud. I want to say something before we start. I'm aware of my slow speech, and I wish I could offer better. I wasn't always like this, but after 2 full courses of chemotherapy plus 1 course of radiation therapy, there's an upside. I'm still here to speak. And the downside is I struggle to get the words out, along with a little neuropathy in my feet. Other than that, I'm doing quite well. The lesson here is I'm still getting off my butt and fighting for the truth. And to all of you, my friends, I say never give up and never ever let anyone silence you from expressing your thoughts and following your dreams. So let's get right into it and start establishing our first question. Is the habitat established on a ball or plane? Remember, all we need to do is rule one impossible and the other wins by default. Then we'll be able to answer our second question. What separates light and darkness, day and night? To do this, we must first have the answer to question 1. Can you see the gradient in the sky between the light and darkness? Well, it's moving with the sun, and it's the final separation of light and darkness. And this can only happen on a flat Earth. This image is a hallmark of final light as it fades toward the horizon. It takes place 1.5 hours after sunset. It's nearly always seen at last light. See the orange lower atmosphere? It's very significant. It couldn't be witnessed on a globe because it occurs 1.5 hours after sunset. And in that time, a globe has rotated 1,500 miles deeper into the Earth's shadow. And that 1,500 miles equates to a 280-mile-high curvature problem. And this orange glow requires direct intense backlighting. The intense direct backlighting is only visible on a flat plane, where the sun is horizontally positioned in a direct line of sight with the spectator. So why is light decreasing on a flat plane? The sun is beyond the observer's limited line of sight. Its light isn't affected by the spectator's limitation of perspective. However, light has a limitation, and that limiting factor is the law of inverse square, which says, as distance increases, light intensity decreases, and on a spherical ball Earth, geometry shows that there would be a 280-mile obstruction blocking the view of this last light event, among other problems. We'll look at when and why we see an arching of the light, and why we see it on a flat Earth, and why it's not possible to see the same on a globe Earth, having to deal with a curvature and a shadow problem. I'll play a time lapse that I took from sunset to last light. It's condensed down from 1.5 hours to 20 seconds. I want you to keep in mind that the image you're seeing on the screen right now was taken 1.5 hours after sunset. It's about 15 minutes before the light is completely gone. A globe has spun east at a rate of 1,000 miles per hour and is nearly 1,500 miles past the terminator line into the shadow, and has accrued a 280-mile-high mound of curvature between his current location and the terminator line. I want you to really stop and think about this for a moment. If you come back with, it would be impossible to see this, you'd be right. On a flat Earth, this would make sense. The sun has receded 1,500 miles after dipping down below our perspective horizon. But just because it's moved beyond our visual acuity doesn't mean the sun has dropped altitude. No, it's still at its 4,000-mile elevation, and it's still passing light to our eyes, and it's backlighting this image. Of course, on a ball, this isn't possible. I'll have some graphics to demonstrate this in a little while. I'll really simplify how impossible it would be to see this image on a ball. Okay, this is my own footage. Now watch how after the sun sets, how the light, you can see it move down toward the horizon in an arch. I'll play that a couple times. You can see it as it's moving out of sight. That's the edge of the field that I was talking about. And you're seeing the inverse square law in all its glory happening right before your eyes. And there's the arch. And I'll try to explain where that comes from later. Think about this. A spectator must see the base point of the terminator line to see the image in the lower right of your screen at 1.5 hours after sunset. He has a 280-mile high curve obstructing his view, and the terminator line is, well, who knows, maybe 1,000 miles above his head. I'm not smart enough to calculate that distance, but it's a lot higher than the 280-mile curvature that you see between the two diagonal red lines. This graphic represents the field of light on the flat plane. If we were going to test the distance sunlight can travel, we'd need a large flat space like our Earth, and it appears to me that light has a limited reach of about 6,000 to 7,500 miles. The outer gray area around the field of light is about 1,500 miles and represents the time from sunset to last light, and it happens over the last 1.5 hours of sunset. Now I've added the symbol for the inverse square law because I think this is the underlying reason light intensity decreases. But it might be that a photon has a limited time of existence, which would be a fraction of a second if light travels as fast as we're told. I believe the arched appearance of the last light is caused by the spherical nature of the light emitted from the sun, and it's shining on the firmament above, similar to shining a flashlight on the ceiling. With our limited narrow field of view, the domed firmament above appears flat because we only see a small section of the whole. But as the light moves away with the sun, it follows all the known laws of perspective, thus appears to equally shrink from all sides. Here's an example how perspective looks in a dome. As the final field of light moves further off into the distance following the sun, it's moving right along with the sun, you would see this image on the horizon, and it would fade away gradually. We'll talk more about why it's only possible on a flat Earth to see the orange glow on the horizon an hour and a half after sunset. On a flat Earth with no curvature, the 1.5 hours and the 1,500 miles that the sun has traveled supports all the visual effects that we actually see, like the horizon stays brightly illuminated with backlighting from the sun, and the light steadily diminishes as the sun's distance increases, and it carries the field of light with it. Here's an example of the outer ring of light on a flat Earth, where light intensity is gradually reduced to darkness. It's about 6,000 miles from the sun to where we see the sun set. And it's an additional 1,500 miles to the last light. And as the sun continues moving away at 1,000 miles per hour, the light steadily diminishes away. On a flat Earth, we have no 280-mile high wall of curvature and no Earth shadow, and we continually have backlighting from the sun, and we need that in order to see the light fade at 1.5 hours after the sun sets. And now we have an example of the outer ring of light on a globe, the time between sunset and darkness. As the Earth spins 1,500 miles deeper into the Earth's shadow, the curvature is increased to a height of 280 miles. At that height, the sun is obscured and backlighting is impossible, as the sun is behind the Earth. It might be possible to light the highest atmosphere, but not the lower atmosphere, because of the Earth's shadow and 280 miles of curvature. The globe has now spun a distance equal to driving from the Pacific West Coast all the way to Minneapolis, and that's around 1,500 miles, or 3/5 of the way across the continental United States. The sunset occurs on the edge of the yellow area as the Earth continues rotating for another 1.5 hours at a rate of 1,000 miles per hour. The spectator who's watching the sunset is repelled 1,500 miles deeper into the shadow of the Earth, and he's no longer able to see the lower atmosphere because it's in the shadow. The lower atmosphere is the only place we ever see this bright, glowing orange atmosphere with its intense backlighting of the sun. Here's an animation to emphasize the reason why he can't see the lower atmosphere. That 280-mile high gap between the spectator and the lower atmosphere, where the sun's light shines across the rim of the Earth. The spectator is 1,500 miles into the shadow. He can't see the glow of the sun in the lower atmosphere. 1.5 hours has passed before the image in the lower right of your screen occurs. And this baller now has a 280-mile high obstruction between himself and the terminator line where the sun passes over the Earth. He can't see that orange glow. The problem becomes apparent when we interject non-existent spherical curvature onto a flat surface. Though a spectator on a spherical Earth might see a somewhat similar sunset to that of a flat Earth, he would not see a prolonged backlit horizon, and his counterpart on a flat Earth would. And this leads us into another problem with the spectrum of light. It seems to me that light must have a limited spectrum, otherwise a flat surface would maintain some degree of constant light, similar to that with the 24-hour sun, as seen in the northern regions. This is not reality. We've clearly established that on a globe, we couldn't see anything more than possibly the initial sunset, and on a globe, we would not see the final stages when light diminishes over the last 1.5 hours after sunset. I've always liked this little saying, so I doctored it up so we can present it here. Light travels faster than sound. which is why some people appear brighter until you hear them speak. The reach of sunlight is around 12,000 miles, 6,000 in all directions from the center. We know this and can measure it, but the only way to comprehend it is to understand that we're on a flat plane. But it's very difficult for some people to overcome the indoctrination of the globe. I just ran out and sought this for our video lesson. The sun just set a short while ago, and I see this high-flying jet with a condensation trail lit up brilliantly with the sunlight. Why is this happening on a flat Earth, you might ask? Well, I'll tell you what I think is causing it. But it's not the shadow from the Earth between the jet and my camera. The sun's light is limited by the confines of the inverse square law. The jet is flying inside the field of light in an area before the light has made an exponential decrease in brightness. I'm standing outside where the brightness has already decreased. The jet is flying way out over the Pacific Ocean, and the light between us is fading rapidly because it's being inversely affected by the inverse square law. The light between the jet and myself has been squared, and the numbers are so large that we have started seeing notable decreases in light. Large numbers of squares means much less light. It's drastically reduced the visible light. Now that was a mouthful, little hard to comprehend, so let me try to break it down. Now I'm no mathematician, but I'm going to explain it anyway. And this is usually where I get myself into trouble, explaining something that I don't feel I fully understand. But with that in mind, I'll make a stab at it. This is the way I understand it, at least back when I was in electronics class a long time ago. I perceived it like this. You ever wonder why you seldom see the graphic that represents the inverse square law drawn out more than 3 steps? Well, it's because when you multiply a number by itself, it becomes exponentially huge. However, in this case, exponentially increasing the number of squares inversely affects or diminishes the amount of light per square. Thus, we have a reduction in light that at a distance gets exponentially reduced. For example, look at the number between step 5 and 6 on the calculator. The number instantaneously becomes humongous, and then the calculator starts using exponential numbering. And I think between my camera and the jet, we are making one of these exponential reductions in light. So you should try this on your own calculator. Hit the square key 9 times. Oh, oops. I think we just ran out of light. Inversely means as the number of squares increases, then the amount of light per square decreases. So we could say that light has an end to the point where it can't be perceived anymore. Let's visualize what's happening using one of my silly visual aids and see how we would perceive these numbers in the real world. I've stacked the first 5 numbers from our calculator near the horizon. These represent the times we've squared the number, but they are broadly spaced between the point source light, the sun, and sunset. They are not tightly spaced because they don't represent any significant reduction in light. Now I've placed the rest of the numbers on our graduated scale. They're tightly spaced in a narrow span of time because they represent the greatest reduction in light. So visually, they occur much more rapidly from sunset to dark. These numbers max out at infinity, so many squares that we can't perceive any light at all. We see it in the sky as a gradual fade from light into darkness, a gradient. Let's clarify this with using a different graphic. Look at it like this. We'll put the first 5 squared numbers between the sun and sunset. They're broadly spaced because they don't affect the amount of light all that much. Now we'll put the last 6 numbers between sunset and dark at the end of the field of light. These squared numbers are very tightly spaced because they affect the visible light the most. We actually see it happening because we're talking about visual light. I do hope this simplifies the process enough. It really is a simple concept once you see how it works. This is known, accepted science. It's a law that affects not only light, but also sound, gravitation, electrostatics, radiation, and of course, light. These are all waves that are emitted from a point source equally in all directions. With light, we can actually see it, but with something like radio waves, you can't see it, but you can measure it or hear it on your receiver as poor signal. Sorry for interrupting our jet story with technical stuff. Let's continue. I'll demonstrate what I'm saying in a graphic, but we'll also be covering more about the graphic later. Now, observations are important. Let me describe what I saw. I first saw the jet with a brilliantly lit up white tail, but I had to run and get my camera from the bedroom. Only took a minute or two. Now look at his tail. It's not so bright, and it's turning orange. Well, that's because he's starting to come out of the field of light. The same reason the clouds change to orange and red a few minutes after sunset. I'll cover this heavily later in this video, because I'm thinking the color changes are significant. Here's our field of light. Let's zoom in and see where the jet is and where I'm at. Hopefully this makes sense. It's a different concept than what we've all been taught, but it explains a lot on a flat plane about how light works. Like I was saying, the jet was deeper in the field of light and the tail was bright white, but it's turning orange because he's exiting the field of light. I'm already outside of the bright light field. I'm the red dot on the bottom and he's up in the air. Not all of the light stops from sunset to dark. Takes about 1.5 hours until we see a band of light pass overhead toward the horizon. and we actually see this field move slowly out of our sight. What are we seeing here? We're seeing light intensity diminishes as distance increases. In simple terms, the inverse square law states that any energy or force will have a drastic drop-off in strength as it travels further away from the point source. Any source which spreads out in all directions without getting lost obeys the inverse square law. What appears to be happening from sunset to dark is a maximum disbursement of the visible light spectrum due to the law of inverse square. Around sunset, the visible light spectrum drops off until we see 1.5 hours later a graduated band of light fading into the darkness. It passes overhead, then follows the law of perspective. It shrinks into the horizon until all light is gone. And this, my friends, appears to be the limit to visible light's reach. Our sun is not shining through 6,000 miles of atmosphere. I doubt that any light could do that. And it's not going over the curvature of the Earth. We've demonstrated that in previous discussion. Remember, the sun doesn't drop behind the curve of the Earth. It recedes away from us at a specific high altitude. In this illustration, it's indicating that light spreads out equally from the sun, around 6,000 miles in all directions from the center. Then I've placed the symbol for the inverse square law from the center to the edge of that field of light, indicating that light is being reduced, but it's minimal and spread throughout the day until that light reaches the sunset. And it's at that point that we see another field, which I'll call the field of visible reduction, where the light is squared to the point where we see major reduction of light, and over a period of 1.5 hours, that light is squared to the point of infinity, and we can't perceive it anymore. And we have darkness. This is what I think is actually happening between sunset and dark. And it's not the result of the sun being obscured by the Earth. We can see from our previous example that a man on a ball can't see the final stages when light vanishes into the horizon. And this is another of many evidences that we are on a flat, plain Earth.